Now I'd like to switch gear and to consider a parametric setting, which is basically a setting in which I have a linear data generating mechanism. And I'll show you that this setting is actually quite rich and has a few results that may be surprising. And so this is work that was done by Marine Le Morvan with Nicolas Prost, Aaron Scornet, and Julie Joss and myself, and was published at AI Stats last year. And so the setting is we have a linear generating mechanism. Y is a linear function of x, the fully observed data, the complete data. However, we're observing z, which is only partially observed. It's x masked by m. Sorry, I have a change of notation compared to the prior part because I copy-pasted things too fast yesterday. And the first thing that we see is the best predictor, the optimal predictor, may not be linear. And for this, let me introduce a very simple example. I have y, which is the sum of x1 and x2 plus noise. And I have the link between x2 and x1, which is a nonlinear link. It's an exponential function. When I'm observing only x1, I can, the optimal predictor is given by using this formula. And then the optimal predictor is written as y, which is the sum of x1, an exponential of x1. So this nonlinearity is introduced because of the link between the two variables. And because when I'm removing one variable, the best thing that the model can do is use this link. So even with a linear generating mechanism, we may not have a best predictor which is a linear. So we need to add extra assumptions. And basically, we'll make assumptions that our covariates are Gaussian. And we're using a classical assumption from the missing value literature, which is that x conditionally on m is Gaussian. So if I give you a missing value pattern, then there exists a mu and a sigma such that x follows a Gaussian distribution with mu and sigma. And this mu and sigma may be dependent on m, or they may be independent from m. And if they're independent from m, then we're in missing completely at random settings. And now if I'm in these settings, then we can show that the optimal predictor is now a polynomial of x and cross product of m. And the problem is that this polynomial has 2 to the power d terms. So the optimal predictor is really given by a linear function of m, and then to which I will add the combination of m and x, and then I need to add the two-term combination of m and the x's, and each time I have different model coefficients. And we can immediately see the problem here is that we have 2 to the power d terms. So this is a fairly complicated expression. So this is a polynomial, and so I can fit it using a linear model on an expanded basis. And if I do this and I use an ordinary least square, then unsurprisingly, I have a risk, a finite sample risk that's on the order 2 to the power d divided by n. So this tells me that I have a sample complexity with this procedure that scales with 2 to the power d. I need to guarantee a given estimation error. I need a number of samples that is on the order of magnitude of 2 to the power d, and that's related to the complexity of this expression. So this is bad news. And now I can twist the problem, and I can consider the problem as the following. My optimal predictor, my base predictor, is piecewise affine. It's for a given combination of missing value features, it's an affine function. A function that is piecewise affine is a function that I can learn with a multi-layer perceptron with rectified linear units. So rectified linear units are piecewise affine. And so what we can show is that we can apply a multi-layer perceptron with really nonlinearities to the concatenated vector, which is x imputed by zeros for the missing values and m below it. And for this procedure to be consistent, unfortunately, if I have a single layer, which is the setting that we have studied, I need a width of 2 to the power d. Now, the thing is, heuristically, we can reduce this width and hopefully capture some structure in the base predictor with the multi-layer perceptron. So heuristically, we can control the model complexity by reducing the width of the multi-layer perception. So given that, we've run experiments, and there's a lot of information in here, so I'm going to go over quickly. But our experiments show that in missing completely at random settings where imputation and EM should work well, imputation, which is in red, and EM, which is in green, work well. They both at small sample settings and large sample settings, they give us a good prediction. Constant imputation with a linear model doesn't work well. It doesn't work too bad, but doesn't work well. It's not consistent, as you can see here. And what we're doing here with those lines is that we're varying the width of the MLP, the multi-layer perception. And as we're varying the width of the MLP, we can see that we're exploring different trade-offs. And if we have a lot of data, we're better off having a very wide MLP. But if we don't have a lot of data, we're better off not having a very wide MLP. Now, we can do this with more complex data, missing value generating mechanism. And if we do this, we see that our procedure tends to becomes interesting compared to the other procedure. And the reason is that it becomes extremely hard and non-consistent for the other procedures to capture the more complex missing value mechanism, and in particular, if we're in a not ignorable setting. If we're in not ignorable setting, imputation and EM cannot work, whereas our procedure based on an MLP works and converges. So the interesting thing is that we're using a very flexible model, the multi-layer perception. We know it's consistent if it's wide enough, but more importantly, because it's very flexible, it's going to be robust to violations of the model. Okay, so to summarize this part, the linear predictor, even if we do constant imputation and even if we optimize the constant, is not consistent. So if we go back to our previous result that tells us that constant imputation works, yes, constant imputation works, but only if we have a very rich predictor. Even in linear settings, in linear data generating settings, then a linear predictor with constant imputation will not work asymptotically. I can make this better by doing a polynomial of the mask using combinatorials of the mask, but this will incur a large sample complexity. And I can, I'm better off replacing this with a multi-layer perceptron, which is going to be consistent, which if I have no assumption, no structure on my missing value mechanism will require a lot of hidden units, but if I have more structure, will adapt.